Hey everybody, and welcome back to Linear Algebra Online. So I want to start off today and talk a little bit about this again. The usefulness of this is pretty large because what this basically gives us is a way to kind of see if something is not similar. Because it's saying that if something's similar, then all of these things should happen, right, between two matrices. And if you can look at it like two matrices and kind of identify one of these characteristics that they don't have in common, then that means that these are not similar. Basically, it's like the contrapositive, like if this doesn't happen, then this doesn't happen, right? So it's not always super clear, but if you look through, okay, both of these are not similar, okay? And if you look at this one, I mean, if we just check determinant of A, determinant B, right, you can see that this one is going to be 1 minus 4, the determinant, and this one's going to be 4 minus 1, right? And I'm pretty sure that those things are not the same thing. So that is one reason why those two would not be similar. So A is not similar to B. It kind of looks like an X, but it's a not tilde symbol. A is not similar to B because determinant of A doesn't equal determinant of B. Oops, B. So that's that one. This one, okay, if you check determinants, let's say, so we have 2 minus 6 here, we have negative 1 minus 3, right? And so this one is actually true, right? 2 minus 6, negative 4, negative 1 minus 3, negative 4. That doesn't mean that they're just necessarily similar. It just means that they happen to have the same determinant. And if you keep going down the list, you might notice some other things that are actually the same. But in this case, and these are the kind of things too where at this point, like if I was checking some of these, right, like checking eigenvalues, like you would not want to do all these out by hand. I mean, they're not that bad, but you got to think about, like, in the real world, these numbers are going to be insane and like weird decimals, and you usually just use like programs like Mathematica or something like that to get the eigenvalues like really quick. But if you go through it, you know, just down the list or something, eventually you will see that actually D wouldn't hold. So the characteristic polynomials are actually going to be different here. So we can say it like this one, like the polynomial for as a function of lambda for like this first one is just not the same as the polynomial of lambda in lambda for the second one. And so since D fails, we can say that A is not similar to B, just since they don't have the same characteristic polynomial. So that's just kind of a way that we can use this thing. We can basically check these conditions, and if they don't hold, then this implies that they're not similar. So kind of on the other side of it here, if you check this whole list, which I'm not going to go through, it takes a little bit of time, right? You're actually going to see that for these two matrices right here, A through G are all true, okay? And what I just want to make a point about is that having that happen does not mean that A and B are similar. But A is not similar to B. And this just is, you know, this you should read as an if-then theorem. Like, if A and B are square and A and similar to B, then you definitely will have these. But it does not, it's not an if and only if. It's not saying that if you got all this stuff happening, then you'll get this, okay? So you can use it the way I used it in the last problem, where if I find one of these that fails, it will imply this fails, okay? But that's just the contrapositive. So it does not, it's not the converse is not a useful thing here, okay? So that's why it's not an if and only if. Okay, that's just an important little side note. Okay, all right. The main thing I want to really do is start really talking about how we do this thing to diagonalize a matrix. And it's really important trick because a lot of things, we've seen this already, that pop up really nicely if you have a diagonal matrix. So like the eigenvalues, right, should just be on the diagonal for any diagonal matrix. We've seen that, which is going to be one of the big benefits. There's a lot of times you just you need those eigenvalues for something, and you just want to have them pop up naturally in the problem and be able to see them. And this technique will basically do that for us. Powers of matrices are really, really easy this way. You can do the power of A by actually doing a diagonalizable argument, and then really do the power of D, and you're going to be able to get the power of A from that. So there's a lot of cool little shortcuts that pop up in linear algebra if you can create a matrix D that's going to be diagonal. All right, and all it is again is just this is basically just a similarity thing. Okay, so it's saying that if you have a square matrix, A is diagonalizable if there is a diagonal matrix D and that A is similar to. Okay, so before we did a lot in the last video with just similarity between A and B or something, but here we're saying that A is not just similar to any old B matrix, it's similar to one we're going to call D, which this is a diagonal matrix. Okay, and don't forget too that this is just kind of typically how you write it, but you can write that a few ways. You could write it, you could also write the AP equals PD, right? Because P inverse, you could just multiply on the left by P, right? And then kill off the P inverse there. Or you could do, I guess the other one is you could multiply on the left by P, right? And then you'd have AP equals PD. But then you can do one more step, and you can multiply on the right by P inverse. So you can also say A equals PDP inverse. So all of these are equivalent things, right? So I just want to start off and just show you how we go about this. So this is one that we actually can diagonalize. And a big part of what we're going to talk about in the next few videos are how we even know if something is diagonalizable. But first I just want to do the simpler thing, which is just do it. Okay, so this one is diagonalizable. And these are kind of the steps. So to do it, I'm going to kind of try to color code these things here so you can kind of see what I'm doing a little bit better. But this is where we want to use our calculators to start speeding some things up, because the first part of the process involves finding eigenvalues and eigenvectors. And so for this and this, I would just do eigenval to get this stuff. And then we're going to put them into a matrix a very specific way, and basically find an inverse again on our calculator. So let's just do it. So the first thing is find the eigenvalues. This is actually a matrix we saw in the video on n by n eigenvalues and eigenvectors. I'm just going to put them, I think I'll just put them right up here. So we have that there's one eigenvalue that has algebraic multiplicity 2, and it's 0. And then there's another one that has algebraic multiplicity just 1, and it's -2. The eigenvectors, I should say, for the -2 one is -1, 3, 1. Okay, and then so that's for this one. Actually, I just said I was going to color code this, so let me fix this here. Okay, there we go. So find the eigenvalues of A up here, right? Find the eigenvectors of A right here. So this is the eigenvector for -2, and these were the ones we found for the 0. So those are, again, at this point, just use your calculator, get those, okay? Don't need to spend time doing all that work out too. So then I have this step where I'm going to create a matrix where the columns are eigenvectors. This is going to be P. And the order doesn't matter here, okay? And I'll talk about this in a second. So I'm going to create this matrix. I'll just create it this way. So there we go. I created a matrix, okay? And this is going to be P, all right? So we'll just call this P, all right? And the next step is to find P inverse, all right? And again, just do this on your calculator, all right? We would get P inverse as -1/2, 1/2, 3/2, 0, 0, 1, 1/2, 1/2, -3/2. Okay? And then what we're going to do is we're going to just find this matrix product. And again, you can do this on your calculator. If you do P inverse AP, right, all just plug and chug in your calculator, you will get -2, 0, 0, 0, 0, 0, 0, 0, 0. And this thing right here is D, right? It's a diagonal matrix. And what I want you to see is that on the diagonal here, this is where the eigenvalues are going to pop up. And the order is very important. That's what this is talking about. So -2, right, was the eigenvalue for the corresponding eigenvector -1, 3, 1. And that's, if this vector is here, this is going to pop up here. If you do then the 0 eigenvector kind of things here, that you're going to get 0 there, right? If you had flipped it around, if you had put this here, you're going to get 0, -2, 0 on the diagonal, okay? And that's it. I'm going to actually prove this whole thing that I just did too, but what you typically need as like an engineer and a chemist and all these different people that use this stuff is just literally this part. This is like what most people just need to know how to do. The proof that I'm about to go through, that's a very mathy thing. I do want you to see it, but it's a lot of calculator work. It's a lot of just go and compute things and put them in the right spot and do some matrix products, and that's it. And this is just honestly a much nicer thing than this, right? Like this thing that we started with, is now similar to this matrix, and this matrix is really easy to work with. So remember, what all of a sudden we get out of these two, right, is all this stuff. So we just basically did we have the beginning of this theorem, right? A and B are n by n matrices. A is similar to B, well, D here, right? All of a sudden we got all this same info. This is really, really, really useful. And so the purpose of this trick that they figured out was that, well, I don't need to work with this messy thing. I can work with this messy thing for some stuff in math, not everything. All right. So what I want to do just at the end here is prove both directions of this theorem. So this theorem is literally where it's the theorem that talks about why I can do what I just did, okay? So there's sort of two things going on. So I'll break this down. There's a lot of text here. So I got n by n matrix A, and that thing is diagonalizable if and only if A has n linearly independent eigenvectors. So that's one thing that I'm going to have to show, okay? And then it's going on, just to be a little more precise here, it's saying there's going to exist a invertible matrix P and a diagonal matrix D such that that thing pops up, right? If and only if the columns of this P are n linearly independent eigenvectors of A and the diagonal entries of D are the eigenvalues of A, corresponding to the eigenvectors in P in the same order. Whew. Okay. So it takes a little bit, but the good news is that kind of if you go one direction with this proof, the if and only if is pretty natural, comes up the other way too. So I'll talk about both directions here. So I'm going to start actually with, instead of P inverse AP equals D, I'm going to start off with AP equals PD. Okay, I actually personally like that form of diagonalizable similarity stuff a little more. And there's reasons for that you won't really see in this course, but down the road, if you keep taking linear algebra courses, this is a little nicer, but I'm not going to get into it right now. So I'm going to start here, okay, and I'm just going to, so I'm assuming that happens, and what I will need to show, right, is that P here, I have to prove that P has n linearly independent eigenvectors and eigenvalues stuff, blah, blah, blah. So I'm going to use the notation of eigenvalues. So I'm going to use some lambdas in my problem here, but I'm not assuming they're eigenvalues. It's just that I know they're going to become one, so I might as well use that notation, okay? So I'm going to start off and just decompose AP equals PD into this. All right, so what I got right here is I'm basically just splitting P up into column vectors. And then this is my diagonal matrix D. Now, assuming they're eigenvalues, I'm going to show you that they are. And these are just zeros everywhere, so I'm just doing it like that. So what I need to show is that these are linearly independent, and I need to show that eigenvalue-eigenvector relationship sort of pops up here. So this is going back to kind of the matrix column expansion thing that we saw way back in like chapter, I don't know, 3 or something like that. I'm going to multiply this in, and then if you think about this stuff, right, if I do matrix product here, right, I'll have P1. So what's going to happen here, it's a little hard to see, and honestly I would, if I was you, I would maybe make like a 2x2 matrix here and a 2x2 matrix here that's diagonal, just to kind of sell yourself on this. But the way this would work, if you multiply these, this will become just P1 lambda 1, comma, P2 lambda 2, comma, da 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 da. So what you'll get if you multiply all this stuff in is just AP1, AP2, dot dot dot, APN, really I should put vector, vector, vector. So you get that matrix, and then it's going to equal this matrix, P1 lambda 1. Or you can think lambda 1, P1. Doesn't really matter. Actually, yeah, just because it's going to look a little more like what I want it to look like, let's do lambda 1, P1, lambda 2, P2, da, da, da. And then lambda n pm. So if you literally multiply this out, and I think the best way to see this is to like create like actual numerical example, but the way with all the zeros in here it's going to work is that you're really going to get this, which is super nice. So you have this matrix equals this matrix, okay? Which means that this column equals this column, okay? So I'm just going to say like, now note, A, P, well, I'm going to write it all down. You'll get this. So all of those are equal, right? And that means that we've got one part of what we need to show. So we've shown that Pi are eigenvectors for corresponding eigenvalue lambda I, right? So that's important, right? We've done one part of what we need to show up here. What we also need to show is that the columns of P are linearly independent, okay? And I think I can squeeze that in over here maybe. So I would just say since P inverse exists, by the fundamental theorem of invertible matrices, we know the columns of P are linearly independent. And that's kind of it. So, the fundamental theorem of invertible matrices is that huge long theorem we've seen where you have like tons of different parts that are equivalent, and we've really been building it up as the year goes on. It's just, like things like its full rank, the nullity is 0, all that sort of stuff. And so, really the columns have to be linearly independent because if they weren't, then when you like apply the transformation, you're going to lose dimension. And the rank wouldn't be full rank. You'd have some stuff going to 0. All that sort of stuff would be happening. And we will actually, once we build up all the equivalences of that theorem, I want to take some more time and look at it a little more closely. And we may do a kind of proof sort of like problem set where we basically just look at those and prove all those equivalences. But this is basically the forward direction. And the backwards direction is really similar to this. We kind of just like unpack everything. All right, so the backwards direction should be pretty quick. So we're going to start off and we're going to assume this. All right, so all this stuff is basically what we just showed before. We're assuming that A has n linearly independent eigenvectors. They are P1 through Pn here, and they come with corresponding eigenvalues, lambda 1 through lambda n, okay? And so if that's the case, right, then we're basically just working backwards with what we have, because if we have that, then we know that the relations, these ones, right, and those are just what, it means to be an eigenvalue and eigenvector kind of setup. And so then what we can do is we can go, and from there we can create this kind of matrix equivalence, this one. So now what we have is, right, if these are all equal, then we're going to get this sort of matrix equivalence, right? And so then we can like factor basically the A out of this thing, right? And we can factor this into the AP equals PD, right? So we have this, right? So what we got right now is, our AP equals PD, but we also want to show that P is invertible, right? And that's just where the fundamental theorem of linear algebra comes in again. So we know in the fundamental theorem that all of those statements are equivalent, right? So if we have that the columns are linearly independent, which we know, then we can get the very first one in that theorem is that the matrix is invertible. And so that's what I basically use. I would just write this down. I just started writing and I noticed I wrote the wrong thing up here. I wanted to assume not A, but a P, right? If you look at what we're proving this direction. Assume P has n linearly independent eigenvector. Therefore, I can say down here, not since A has it, but since P has n linearly independent eigenvectors, or linearly independent, I'm going to even just say columns because that's the more important part. We know by, the fundamental theorem of invertible matrices, P inverse exists. So I'm running out of room. We can write P inverse AP equals D. There we go. Right, so we can apply P inverse to this thing, basically. And that's it. So it really just unpacks what we had.